Are we live? Huh. We've changed a bit of things. Let's see. Here it's saying it's live and two people are watching. I can kind of see it. It's live. Probably. Um. Alright, I think we are live. So, let's go to my stream so that I can view the chat and all. Say it's not receiving data at a fast enough rate. So what does that mean? Let's see. This changed a bunch of things. Anyways, looks like we are live. We are streaming at a good enough data rate, but I don't know why it says it's not, you know, streaming at a good enough data rate, and for some reason the public view bit is not. Um, the public view for me it's not there, but I can like see from other area that it's working fairly well. Just a couple more. Alright, so we have confirmation that we are streaming. Fine. So this is an interesting one. I went ahead and I just thought to myself, why not let's try some FPGA programming. I've had a bunch of FPGAs for a while now, starting with the Jurassic D10 Nano based on the Cyclone 5. That was way long back. And then I've also had much more recently the 96 volts Ultra 96. Now, there's one simple problem for both of them. They aren't. Alright, I think I cut there. But they aren't very like open source in a way. So, yeah, there it is. Right, so as I was saying, they aren't very open source. None of the FPGAs are, as far as I'm concerned. Like, there's no officially open sourced FPGA, but the iCE standard, so the iCE 40 from Lattice, so the iCE 40 family from Lattice is actually open source. It's a very low power FPGA, so it's not like one of those powerful ones where you can actually run like RISC 5 cores, or or even turn them into GPUs and stuff like that. So it's not super powerful. It's for lightweight applications, and that's what it is. And some people have like gotten it to run at 1 gigahertz, but it's very basic. So that's what I have here. It's there it is. Fairly bad FPS on that camera for some reason. But anyways, there it is. That's the Lattice iCE stick. So that's the development board. Super cheap. So that's what I said. You know what? Let's get started. Some basic Verilog, and there's this reverse engineered and open source. No, I'm not from Germany. So hello from Poland. And hello from Germany. I'm from India. I hope everyone knows that by now, by my with my accent and stuff. But yeah, cheap and easy to use. I'm not going to use it for too long because I'm just willing to kind of move on to much more um, fancier stuff. But just to begin with, the ice storm ID kind of a tool chain is a reverse engineered tool chain for this particular FPGA, and it's completely open source. So why not just use that, and it works just fine. So um, there's always this sort of thing where if you're a software programmer, you'll have difficulty going into the FPGA world, and if you're FPGA programmer, you're going to have difficulty going into the software world, because apparently there's this uh, a difference in the way they are programmed. And I did not really believe that until I actually got this, and let's take it for a run. And yes, it was very interesting. It was honestly, like I have this Blinky application. When I went ahead and ran it and tried to understand it, was the same as when the first time I ran the Blinky Python application on the Raspberry Pi. I was equally amused and I was equally confused as to what's happening, and how does all of this work and how I can go ahead and code it more. So I'm happy to say I've moved a bit further than that, not too much. I have not been spending a whole lot of time with this FPGA. I have moved forward a bit, so let's go, and I really want to show sort of what it looks like in the Verilog programming language. Yeah, let's call it a language for now. There are two standards. There's Verilog and there's VDHL or VHL or something or the other. Verilog is what I'm sticking with for now, just because. So the first one was Blinky, the one that's running right now. Huge time difference between the blinks, so you really need to keep an eye on the LEDs. They will go on and off. So just in a second, this is what the code looks like. I'm going to try to expand that if that happens. View. I can't increase the text size. What the no, I cannot. You know what? Not messing with this. Alright, so this is how it looks like. So the module bit is the name of the module. That's what it is. So you start the module with module, and then there's this top kind of it's just a block, not necessarily a function, but just a block. So you have input, which is your CLK or the clock, which is the external clock in most cases, which happens to be your Lucas. I'm actually running Fedora since the beginning, like since 2 years straight, and didn't even format it. Alright, so the top is kind of a block where you add a bunch of stuff. So what's your input going to be, what are your output LEDs or output pins are going to be, or you can even output to a register or something like that, as far as I know. Again, so instead of having, you can have int, but instead of adding a variable, you add a register. And what that does is it basically creates registers, like hardware registers in the FPGA. You say 26 to 0, so that's 27 bits register counting from 0 to 26, and then there's this counter register, which is like a 1 bit register. Again, this is my first time doing all of this. If you are electronics engineer on the channel watching this, sorry, this is going to be messy and you might just get pissed off. I cannot control that. So always it's sort of a for loop. Again, this is my thinking, how it's going inside my head, because I've been programming, I've been doing structural programming and all of that stuff in C or Python or Java or whatever. It's pretty much the same. So moving on, always is like a for loop, but it always has an input. So always has an input. You need to give it that, and then this is the positive edge of a clock. So the clock goes high, low. So every time the clock goes high, this bit of code is run. So what is this doing is adding the value or the last value of the counter register, adding 1 to it, so just incrementing it and pushing it forward. So that's it. That's what it is doing, and as soon as it reaches 26, it resets. So this is the adder block. So if you have seen a digital electronics kind of a gate diagram of an adder block, this is what it creates basically inside an FPGA. And then you just assign each and every LED to the last bit. So as long as the bit 26 is high, it will be on, and that is what happening. So it counts from 0, 1, and then goes It goes 0 1 and then 1 0 and then 1 1 and then 1 0 0 and then 1 0 1. It does the binary counting stuff, and for as long as the 26th bit is high, the LEDs remain high, and that's how it works. So interesting stuff. You don't see the editor. Oh, okay. Is it this one? Now you can see the editor. Alright, so this is the top module I've been bragging about. This is the register initialization. This is the always thing where you always kind of a block, which is sort of the for block, and then this is the positive edge clock. And yes, sir, I just fixed that. Now you should be able to view the code. Wait, let me check if it's fixed. Yeah, it's fixed. It's fixed. Sorry about that. And this is the assign bit. So you assign one LED to the counter. You don't like just go ahead and equate it. You assign it. But when you are inside the for loop, for some reason I've not understood this yet, but inside the always block, you go ahead and just use this, just equate it, or use the arrow bit, and when you're outside it, it's always said to use the assign bit. I don't know why, but that's what works, and that's why we're here for it. Right, so that is how it's working. It's counting at 12 megahertz, and as long as the 26 bit is high, it remains high. What we can do is to kind of make it go faster, count it ahead by 2, and oh wait, I should have actually opened up the blink itself. So blink.v, same program, and then just increment it by 2, control X, Y, and it's as simple as make and make sudo prog. Now you can see it says 163 megahertz. I'm not sure why it's doing that. And let's actually do this. Add my password. What is it? Can someone in the comment section guess my password? That's a pretty bad idea, I guess. Anyways, so now it should be a bit faster. Is it? Maybe. It is programming, but yeah, even making it faster is not as fast because reasons. Let's move it down to 24 bits. This should make it go faster. And make what? Okay, yeah, that would make sense. So now that I've reduced it to 24 bits, I should also remove the thing I've added here. So Sal or Sai, I'll come to your question in a bit. Yeah, that goes much faster. Wait, let me just show it to you. Alright, so yeah, it is going much faster. Now, if you guys can notice, it going much faster. It is certainly fast, but fast. Alright, so Sai asks, bro, you ported out Android TV for Raspberry Pi 3, but why did you never optimize it to actually work? I was never in the area of optimizing it. Someone else was doing that work, porting it. I just pushed out the builds and managed the community. So first of all, there was very little interest from any external developer to do that, or even the Raspberry Pi Foundation themselves. So the developer who was doing the whole porting bit decided to just call it quits because he wasn't getting anywhere, and no one else externally was helping. There were a few people who were helping, but that was not like a very heavy amount of helping to port that. The second part is The VC4 driver was still in its very early age at that point. I don't think it still has Android extensions enabled. The Raspberry Pi kernel also I don't think has Android extensions or the APIs enabled. Or I don't know if the upstream version is now capable of doing that. I will have to take a look. As for the Android TV bit itself, I'm kind of working on it to get like a general x86 Android TV build, but I really want it to be a bit more permanent solution. So let's see where that goes. Alright, so with that said, that's the first, but that's just blinking, right? I mean, if you have to blink individual LEDs, it would be much easier. So you'd think it's not. Alright, official gaming ad. I'll come to it after this code. Again, let's see. So which was the one? The next one is called I think it was the binary counter, and I'll show you all how I got there. So this is the binary counter, and what I've done here is, let's actually program it so you guys can see how it actually works. And also, I know I'm not showing the code, so just be patient about that. So the nano make file, and just go here and add bin counter, and that should be it. And make prog. Alright, so yeah, it is counting in binary. So it goes that's bit 0, so 0 1, wait, let it finish and I'll follow it. 0 1 1 1 1 1 1 1 0, and it moves forward. So it's just counting in binary, right? Now in the make in the file itself, let me remove that. We have two clocks. So the first clock drives the second clock, and the second clock is what I'm using. So instead of every LED going on every second, the second clock actually is a 5-bit register, which basically drives the 5 LEDs. So we are binary, so each of the LEDs is dedicated to an individual register, and that's how it's driving it. So the test register, and here the last line says each LED, so this is bit 0, so this LED 1 is bit 0, LED 2 is bit 2, bit 3, bit 4, and bit 5, bit 1 2 3, yeah, so 0 to 4 actually. And then we just assign it to test. And what do we do? And that basically gives us this pattern. So instead of having a LED then react to a variable like you would do on a software, you just assign the LED to the register, and inside the hardware that actually directly connects the LED to the hardware, instead of having to run a code like equal to kind of thing. So I actually, that's true, I'd side with that. The streaming bit was a bit sad. Okay, removing that. Right, so official gaming TV, depends on what SPC you have. Debian is a good OS. Fedora has also started supporting a lot of OS. They also have an IoT build now, so if you want to go and check that out, just Google Fedora IoT. And apart from that, you can use Arch Linux, that also supports a lot of ARM64 OS. The ARM64 OS support is amazing, but it truly depends on what SBC you have and what do you want to run on it, and if the support is there. So maybe the support is there, maybe it's not, maybe it runs, maybe it's not. Cool. So So that was the binary counter, but that was an accident. What I really wanted to do is to have this have the LEDs move in circle, and what my programmer mind went ahead and did was to just like kind of run a for loop. So this is a for loop for me always, and just increment it. And I was like, okay, I'll increment it, and I had actually um, you know run it as a for loop, and that should work. Nope, it turns into a binary counter. So apparently binary counters are easier to make on Verilog than LEDs moving in circle, which makes sense. So let's see what the LED moving in circle looks like. So this is the code for LEDs moving in circle, and it has a lot of stuff in it, right? We'll just have it be there. We'll come to that later. Remove the binary counter bit, and go ahead and add circle. Flashing that, and this is how it works. LEDs are moving now in a circle, which makes sense. Cool, let's take a look. Now what I did on this one is in the test kind of a clock where I incremented it, I had a little if statement where it would kind of increment on itself, because that's how you like shift each bit, is just to add the previous result. So if you add 1 to 1, it will become 1 0. If you add 1 0 to 1 0, it will become 1 0 0. So your bit moves from its place, and that is what it's happening, right? But I've used if statements, and that's a bit more programmer-y kind of a thing. Yes, I am using the mechanical keyboard. That's more of a programmer-y kind of a thing. But if I actually exit that, there is a way to do it without using the if statement, and that is very interesting. So if you take a look at the circle v2, there's nothing like that. Instead of if statement, I've just added one extra bit in the test variable, and what I've done is just once that's like at 1, it adds it to the rest of the equation, and it just resets it back to going from 0 to like shifting the bit, and as soon as the last bit is 1, resets it and adds it on. So there's a way to actually kind of visualize it. So that's called Yosis. That's the kind of a simulator, so I can read it. So read and circle 2.v. Wait, was it? Oh, okay, read Verilog. And then show. And that would give me a diagram kind of a thing. Right, and here you can see how it's working. So test goes into 3 or 4 kind of 3 areas. It adds on itself, and then goes back, and if and the 4 registers are actually divided, the 5 registers are actually divided into the 5 LEDs, and then the 5th bit, as soon as it goes to 1, so that's the adder part. If it's 0, then it doesn't affect the result, so this Y moves on. If it's 0, it moves on back into the test register, and if the 5th bit is 1, it gets added, resets all the other bits, goes back and follows through. And this is the second timer right here that kind of affects all of this in terms of clock. Yeah, but if you look at this one, how the if statement behaves, we can read Verilog, and what was that, circle.v, sorry about that. Okay, and show. Yeah, that's a bit more complicated, because here we have this is what's acting as an if statement here. These bits, if not equal to or if equal to, that's the annotation for that. Goes in, does a bunch of stuff, kind of confusing. um is there any good free VHL DLID? I don't know. I've just gotten into it and I've only started using Verilog. um yeah, I mean, everything you just have to pay. It's that kind of a area where it is costly and you have to pay. But for larger companies, it's always worth it to prototype your hardware before you send it to a silicon manufacturer, and that's why they end up paying big buck for it. But I don't really want to talk into it. Everyone has their own kind of a business strategy or something, and that's how it is for now. I hope people start reverse engineering these things, and then we'll have better things in life. But for now, this is what we have. LEDs running in a circle. That's our life now. Alright, I think an old official gaming TV. The thing is, SBCs and Nvidia just takes one. Good on you. You got that. So, kind of a expensive stuff. Nice. Um, yeah, I mean the GPU on the TX1 is fairly supported with the open source drivers, but Debian uses a very old version of kernel, and I'm sure Fedora supports TX1. You know what? You asked it. Let's just check it now. So, Fedora uses the Fedora installer, which is called the ARM Fedora installer. I don't have it installed live, but I do have the script kind of a thing. So let's go into CD home and then ARM Fedora installer. Is that what it is? ARM. Oopsie. ARM Fedora. Wait, is it not here? What? Fedora install Fedora installer. No, I have not fiddled around with OpenHab. I'll take a look at what that is. If it interests me, maybe soon, but I don't know. So this is the application Fedora uses to create the SBCs, and we can see supported. So TK1 is there, but I don't see an X1 right now. Maybe it's supported in the future or not. I don't know. The best use would be to go into the Fedora forums, Fedora ARM forum, and just ask what's the status and when it's going to be there. Cool. All right, moving on. So that's the story of just moving the LEDs in a circle, and how you just end up using if statements and stuff like that, where you can actually just do it in a more digital electronics way kind of things. That was that's like, all right, home automation thing. I'll take a look. But yeah, the last demo is called what was it? It was an interesting one. It's called it's called Trail. This is kind of let me just it's an interesting one. So what it does is okay, nano. Let me just show you all how it works. And make and sudo make proc. So the way it works is the LED kind of trails itself. So it's turning on in a circle, tracing itself, and then it turns off in a circle tracing itself, so the previous LED is always on. Now the code is for it is fairly complicated when you look at very log kind of a way. There's a lot of if or else going. It's checking if the last LED is on or if the last LED is off. This is the not symbol, so if this test is equal to 0, this is the not symbol, so that's mean the whole test register is just 0. And yeah, so it's just checking if the last register is full, then it goes in one direction and turns everything on. If the last register is empty, it just goes in the other direction, and there's a flag variable which checks which direction the LEDs are kind of moving on. So that's how it works. But the yours is actually pretty interesting for this synthesis. So read, and let's go to Verilog and trail.v and show. Interesting and confusing. Now I have to still go and remove all of these if statements if I can, pun intended. But yeah, so there's the equal to kind of if statement going on here. So if it's equal to 1 or if it's equal to 0, that's how the registers or the logic internally forms. And I know I'm not showing it again. Yep, there it is. So this is the if bit. This is how the registers are formed for if statement, checking the flag variable. So if it's 1 or if it's 0, just has a adder there. And then there is more if statements here, checking if the trace or the test is 0 or not. And this is testing if it's positive or not positive, and then subtracting it when it's like going on the other direction, and there's this adding it when if it's going in the right direction, if it's turning on or turning off. And it's just a mess of things. And if you're interested in kind of learning all of this, you need to learn how to read this. I don't know really well, but as far as I know, this is how it is. Maybe I'll know when I practice more. So there are a few commands to actually improve on your code from the synthesis structs. So let's see where it was. The flatten one, or so f flatten and f reduce. That's what I'm going to use. Let's see how it affects. And now if you see it, it's going to be very different. So it's much denser. But what the synthesizer program has done is to actually go ahead and enable all of the registers that are in the FPGA, whether they are working or not. They just go and enable all of them, whereas my code didn't. And this is useful if you are using much more complicated programming. But in my case, as much as I want, it's okay. It's not really useful. But anyways, this is how complicated it will get on this FPGA at one point if you just use everything. It's just pretty weird and awesome. So cool, I guess. That's where the stream ends, because I've not honestly worked on anything else since I got this. Pretty busy. You know what? This chat is actually getting pretty interested. So if you're not interested in anything else than FPGA, then you might kind of go. But I'm going to have a bit of chat with the viewers and see what discussion is going on. The Sai says my Pi 3 is broken, Wi-Fi, HDMI, and I'm still using it to run a home server on it. Works just fine. Could be, but like sort of what my experience with running a 24/7 NAS or a home server on a Pi 3 is MDZ. So that's one of the things. is a corrupt SD card. How often that happens, and the other one is I've had both the Pi 1 and Pi 2 twice. Actually, the Pi 2 was a two-time event. Have their power supply area, power supply chips, the regulator, everything else just blown to bits in 24/7 conditions. Right now, I'm using a ROC 64 um, server that just connect to a 4 terabyte hard drive, and I'm just using it as a nice NAS drive. So you know what? Let's open to questions. If anyone has any more, you can kind of chat, see where this all goes. And if you are interested in the Verilog code, here it is. Take a look if you want to take a look. Cool. So I guess I'll just wait for a couple of minutes. If there aren't many questions, then I'll probably log off, go to sleep. It's about 4:30 in the morning, and I'm awake. Live streaming. Nice. Cool. Oh, I need one suggestion. Go on, speak up. Let's see how it rolls. Bye from yeah. Bye official gaming TV. We'll see you I guess later if I end up doing another video at some point. Wow. I mean, two devices per student ID, so you're just allowed to take like a phone and a laptop or something like that. You know what? I'll actually have the FPGA screen on. Um, Wait, who's talking about Wi-Fi again? Oh, so there's some previous chat I'm missing. Um, yeah, I think that would be possible. Yeah, OpenWRT is fairly um, well open. You know, you can modify it a lot. It's not like a regular router. Throw it into a Raspberry Pi or any other single board computer and add a kind of a second Wi-Fi dongle, or even add two Wi-Fi dongle, and it should work. Now it might be a bit slow because of the limitation of the USB speed on the Raspberry Pi, but I'm sure it won't be slower than what you get on your college campus, actually many times. And then once you have that, just connect as many IDs through that IP, through that router of yours. But I'm thinking, if you have by Lucas, it also depends on what kind of an identification thing they have, because my college had a, you need to go and log into a web page, and then log in there. So if you are logging into web pages from different devices, then it's back to square one, because you can't log in from more than two devices. But if you log into that web page from your router, so say the Raspberry Pi, um, yeah, use a OpenWRT compatible router. That would give you much better bandwidth. And make sure it's kind of powered by battery or something, because I'm not sure how you are planning to do it, if you're always going to sit in class, or if you have a spot where it covers most of your area, or if you're talking about your room, if you're living in a hostel. But anyways, log in from that OpenWRT Wi-Fi router to the college Wi-Fi, and then kind of forward it. Should work, as far as I know. I've never really tried that, and because I've never really taken more than two devices to a college, I'm sure that's not, we didn't have any kind of a restriction or anything. Well, if it's for your dorm, then it's fine, because like one of my friends has this issue where um, they have only wired connections in their rooms, and people use a router, and that works fine, up to like as many devices as you want. And yeah, I think that's a good idea. If you're limited to that, maybe try it out. Yeah, just choose the Wi-Fi, the WRT compatible routers a bit wisely. They do have a very, very in-depth kind of um, guide to buying your own hardware. Sadly, my router is incompatible, so I'm looking to change that one or make one on my own, from my SBC or something. We'll see about that when the time comes. But yeah, I mean, it's a good bet. Cool. All right. So actually, I hope that solves or somehow partially answers your question. I'm actually going to go and take a nap, because it's 4 a.m. and I'm planning to get some work done tomorrow. And see you all in the next one, I guess. Bye.